that would not be inappropriate either. I believe that there were quite a number of people who had questions over the homework, or with a homework. It's worth pointing out that I would definitely be doing your homework on your workbooks alone rather than looking and finding answers. This next test will have more conceptual workbook problems on it than the previous tests. So even probably than the ones I gave previously, I'm going to emphasize the workbook and the concepts and the kind of quizzes we did on class Monday, we did on Wednesday, the quicker practice quiz on Monday, the quicker quiz on Wednesday, and then we'll go over some quicker practice, quicker quizzes today. So I would take this workbook very seriously, and along those lines, we went through the material fairly quickly in class, but so if there are questions, I'd be glad to entertain them now.
My question on 33 on the back page.
33 on the back page. So 33 says a hollow solenoid is wound as shown. So what have we got here? We've got, can anyone imagine there's a coil of wire that's wrapped around a region of space? And if we treat this as an ideal solenoid, what kind of field do we create?
Magnetic field?
We create an
Uniform?
a uniform magnetic field inside the solenoid, and we're going to assume that there's not a magnetic field outside. Which direction does the magnetic field go? See, we need to figure out the current first, right? See, that's the positive end of the battery, that's the negative end. So the current is going in this direction. The current is going around the coil this way. Everyone see that? So the magnetic field, if we wrap our fingers in the direction of the current, our thumb right hand, our fingers will point in the direction of the magnetic field. Now, we have 2 electrons going into this. Number 2, and electron number 1. What is the force on electron number 1? Is that the question?
What?
All right, so it's getting deflected. Will it be deflected if there's a force on it?
Yes.
If there's no force on it, will it be deflected? No. So, our magnetic field is to the left, the velocity is to the right. Is there any force on that electron?
No.
Is it deflected? No. No force, no. Electron 2, the magnetic field is still to the left as it enters the field. The velocity is in this direction. So let's see. V cross B gives us a force into the page. But I get the wrong answer. Why? Negative. The force is in the opposite direction. It's out of the page. Does that make sense? It kind of combines everything we know. A little bit about circuits, figuring out how the magnetic field's created. Then we have to figure out the force on a moving charge through that magnetic field. Any other questions?
32.
32, gladly. 32. Oh, this is what you'll do if you go to physics 3. we have high energy physics experiment in physics 3. All right? So our neutral charged particle comes in, it breaks into a positive and negative particle, and one particle goes this way, and one particle goes this way. Number 1. How come particle 1 isn't deflected? Is it moving through the magnetic field? The original particle?
Yeah,
Why isn't it deflected when it moves through the magnetic field?
it's not a charged particle.
No charge, no charge. There is not a magnetic force, even though it's moving through the magnetic force field. Excuse me. Which way is the field? B is into the page. Right. Then, what is the sign on particle 1, and what is the sign on particle 2? Well, particle 1 is moving initially with velocity in this direction. They're both moving with the velocity initially in that direction. They might get a little component when they separate out. What direction is the force on that particle? The force on particle 1 is towards the center because it's accelerating towards the center. Force on particle 2 is towards the center of the circle because it's accelerating towards the center. So we have B into the page. So B is up, B is into the page. If we have a positive charge, the force eventually will be to the left. So which particle would be positive? 1. And the other particle's got the force in the opposite direction, so force on it is negative.
Did you just do part B of 34? I'm just wondering how to get magnetic force in
Part 4 of 34.
B.
Alright, so 2 protons are traveling in the direction shown. So, can I erase this? Is that okay? Draw and label a magnetic force on each proton due to the other proton. Explain how you determine the direction. All right, now, this causes me some confusion. Which one's the source and which one's the object of interest?
Yes. Yes.
I heard both, but that can't be. I said something isn't. Right, we treat them as 2 separate cases. In one case, this will be the source, and this will be the object of interest. In the second case, this will be the source, and part B will be the object of interest. Now, what kind of field does a moving positive charge create? We have a moving positive charge. What type of field does it create? It creates a magnetic field. Is that it?
Correct.
It's still a charged particle. It still creates an electric field. And actually, it probably has mass, so it's probably also creating a gravitational field. We neglect the gravitational field. Why? It's really, really small compared to the electrostatic field. As strong as gravity feels to us, once we get a significant amount of charge, if we looked at atomic scale, gravity is so small that it's not really significant. So, in this case, though, we will be worried about the field. So let's right now create the left proton as our charge of interest. We have to look at the fields first. We can't just skip to part B. We have to look at the fields created first. It creates an electric field here, doesn't it? It's pointing out, the electric field from this particle is actually pointing out in all directions. But at our point of interest, this is the source field created by this proton here. Which direction is the magnetic field? We look at R. What is R in terms of magnetic field? It's the same as R for the electric field. Now R, in both cases, is from our source to our point of interest. So we have our velocity of our source charge. We have R hat. If we think, remember Biot-Savart's law, we have our velocity of our source charge, we have our position vector, we have R cross V, which direction, V, excuse me, V cross R hat, the direction of our magnetic field at our point of interest is therefore into the page, since we have a positive point. So our B field into the page. The other way you can figure out the direction of the B field is put your thumb in the direction of the velocity and wrap your fingers around it, just like we do for a current. B field is into the page here, it'll be out of the page over here. It'll be from our left to right, front of the particle, and it'll be from right to left. Does everyone understand how I determine the fields? And then we could do the reverse, using this as the source, and this is the object of interest. Now, does the electric field created by the left proton create a force on the right proton? Yes. In fact, we know it will be Q force electric equal to QE. So, force from our electric field will be in the direction of the electric field. What about the force from the magnetic field? We now have this proton with a velocity downwards, a magnetic field into the board at that point from the source charge. We have V. V is down, V is into the board. Our magnetic field's in the same direction as the electric field. And our total force is some of those.
So can you say that, like, when the proton is moving in the upwards, you can say that's kind of like a current for deciding how the magnetic field?
It is. At
You're
that,
saying before, like, you can use like your its velocity, but
we can use either. We can treat it as a small current moving upwards,
yeah.
and that tells you the direction. Or you can use Biot-Savart's law, which is, your constants times V cross R hat. V cross R hat. Both ways you'll get the same answer in terms of direction.
Are the magnitudes of the electric and the magnetic the same?
Probably not. I just guessed relative magnitude. Probably depends on how fast they're moving, right? If they're going really slow, the magnetic field's smaller. If they're going really, really fast, the magnetic field's bigger. If it gets close to the speed of light, the magnetic field will be really big. keep that in mind. There's that discussion. Any other questions about the workbook?
31.
What's that?
31.
31. Let's go back to here. Ah. This is actually an experiment. What have we just created? These are big plates, another plate. Created a circuit, created a capacitor here. Actually, this is a lot like the old ATVs. Now we fire a photon. Which way, is there any force on that proton as it moves into this capacitor? So we have a moving charge through an electric field. Does that create a force? Still a charged particle in an electric field, the force is still Q times V. Which direction is the electric field inside this capacitor? Downwards. So will there be a force on the proton when it's in the electric field? Yes, and it will be in the direction of the electric field. You have a positive charge in the direction. Now, the question is, can we create a magnetic field here to make the electrons go through there straight? In other words, can we create a magnetic force that is equal and opposite to electric? Which direction would that magnetic force need to be?
Up.
Velocities to the right, we want the force to be up. So which direction does the magnetic field need to be?
Into the force.
It needs to be into the stage. So that V cross B will give us the force upwards. That make sense? Any other questions about the workbook? Get these down. Get these down. Understand? One more. 24. 24. All right. Did everyone understand 23? Let's do 23. Twenty-three is kind of interesting. So we have magnetic field that moves uniform and moving to the right, and we have magnetic field that's moving to the left. It's uniform. What on earth would create this? We could have. Do we have two solenoids there next to each other? That's one possibility. There's actually a more straightforward solution towards creating these magnetic fields if we analyze these three loops. So what is actually happening to create this? And that's kind of a fun thing to think about. Can this actually be made? So we could do it with two solenoids, but there's another way to do it. Let's see if we can discover through Ampere's law what's happening. We're going to draw a square loop. We're going to integrate them in clockwise direction, and we're going to calculate our line integrals along each leg. Our magnetic field was 2 Tesla, right? 2 Tesla. If we integrate d dot dl along the left path, what component of the magnetic field is in the direction we're integrating, moving? Which the magnetic field is to the right. We're moving up. What component of this field is in the direction we're moving? Zero. So what's the line integral here?
Zero.
Integral of v dot dl equals 0. What about here? We're now moving in that direction, so from left to right. The magnetic field is left to right. What component of the field is in the direction we're moving? All of it, right? So now our line integral will be 2 Teslas over 1 meter, or 2 Tesla meters. And when we go down, 0. And when we move in this direction, now the magnetic field is in the opposite direction of our motion. So our line integral is -2 Tm. What is the net? What is the closed line integral around that loop? 0. So our closed line integral
So there's no current.
equals 0. So what current is there here?
None.
None. The same thing happens when we do the box down here. Because here the magnetic field and our direction are opposite, so we get a negative. Here they are aligned, we get a positive. They add to 0, and we're 0 along those two paths on the sides. But what happens in the middle? What do we get on the left and right legs?
0,
0, 0. On the top, positive 2 Tm. Positive 2 Tesla meter at the bottom, because again we're aligned. So now there is a net current. We notice that as we bring these sides together, there is a sheet of current. There must be a sheet of current coming along that line. So if we create a sheet of current coming at you, so we have a long conductor that's a sheet, it will create a uniform magnetic field in one direction above the sheet and a uniform field in the other direction. If you bring 2 solenoids together with current going in the opposite direction, the bottom of those 2 solenoids look like a sheet also, right, if you get small enough. But if you have a whole sheet of current and you're relatively close to it, you'll have a magnetic field moving one direction on the top and one. So, how many of you thought about that when you solved this problem? Try to think about things. What on earth would cause this? I know it's hard when you're in the middle of the. So that was the point of bringing this up. It also takes a little bit of the mystery out of calculating these line integrals. People kind of feel like, how do people feel about the line integrals? Absolutely solid now for what we're doing in class. Still very mysterious. Want lots more practice. Okay. So it looks like a mix of pretty comfortable. Now, let's go to the question that was asked. It's very similar, but not linear. Now our magnetic fields are in a loop. So what do you think is causing these magnetic fields?
Some sort of wire.
There's probably some current here going into the page, wouldn't you think? Yeah. Now, we calculate our line integral from 1 to 2. What direction is the magnetic field along these points? It's always upward, isn't it? Yeah. And our direction of motion, where we're integrating, is perpendicular. So what is the line integral from 1 to 2 of v dot dl? 0. Integral v dot dl equals 0. Then we're going to move parallel. I think it goes all the way over, doesn't it? To our magnetic field at point along this line integral, our direction and the field are aligned. So at every point, B dot dl, the cosine is just going to be BL. The angle between them 0. So our line integral will be equal to B times L. But what are B and L? Let's see, at that level, this was 4 Tesla. This one out here was 2 Tesla. Did it tell us what the radius was? 1 centimeter? R equals 1 centimeter. So, our B was 4 Tesla, and what was our length? We've gone half a circle, wouldn't that be pi times 1 centimeter? Or if we wanted to convert it to meters, 4 Tesla times pi. And then from 3 to 4, what's the line integral again? 0. Does that help? These workbooks are valuable. I really, really, really encourage you to work on your own. If you don't understand them, come ask questions. I know a number of you came to ask questions. For a couple of people, it was very nice. The light bulb went off. Good to see that. But don't just look up the answers and write them down. We solid? Now, we're doing something really very different than we've done up to now in fields. And so far, we've really been talking about static fields and the forces on a object. Really what we've been doing is saying the static. We've done a little bit of kinematics where we said that we've kind of not talked a lot about the fact that as that particle moves through the field, things might be changing. We've said that for the most part things were static or quasi-static. What we're going to talk about now, what we're really starting to do is say, how does that motion affect the field? Well, it works out with electric and magnetic fields. The static situations are part of the picture. When things change, things become very, very interesting. And here is the problem. We've said that in different reference frames, everything should be the same, right? So if we measure something in one reference frame and we measure something in another reference frame, we should get the same answer. But here's where the quandary starts to show up. I'm a positive charge moving in a constant velocity of this direction. Do I create a magnetic field? I'm a moving charge, I move. But, so you're in the stationary reference, but Luke is in a train who's moving at the same speed as me, and so he's in the same reference frame I am. In his reference frame, am I a moving charge? No. In his reference frame, am I creating a magnetic field? No. So it appears that we have a problem here. There is a way out. Well, I'll show how we escape. But it starts to introduce the idea that there's something deeper going on. There's something a little mysterious, even more mysterious than we thought. So let's go back to Ampere's law of motional EMF. That's our lecture from last time. And look at where we left off. The beginning of the solution starts right here. We had this bar. It's in a magnetic field. The magnetic field is into the board. And now we're going to have this bar start to move. when it moves, we know since this is a conducting bar, there's positive charges and negative charges. What happened is we realized that there is now positive and negative charges moving to the left. There's a magnetic field into the board. The positive charges have a force that pushes them up. The negative charges have a force that pushes them down. And they separate. But when they separate and they move to the opposite ends of this conductor, it creates an electric field that has a force that tries to pull those charges back together. So we will hit an equilibrium point, if this is moving at a constant speed, where the force, the magnetic force pushing up on the positive charge equals the electric force pushing down. So let's draw a quick free body diagram. For that positive charge, we have force electric equals Q times E downwards, right? And we have force magnetic equals Q V, that's velocity, cross E. Everyone comfortable? If it's in equilibrium, that would mean that A equals 0. Then this magnitude needs to equal that magnitude. What do we know about the strength of an electric field inside of a capacitor of length L? We know that if there's a potential from this point to this point, that electric field, if it's uniform, wouldn't that electric field be the change in potential over the length? Electric field. Is everyone comfortable with that? Now let's solve for delta V. The Q's cancel. Oops. And we'll have VB velocity again. VL times V. What is VLV? This will be the change in voltage, so it'll be the voltage that's actually generated as this bar moves through the magnetic field. I want to think about this VL, and I'm going to rewrite it in a little bit different way. I'm going to write this V times time times L all over time times V. I can always multiply by T over T, can't I? T over T is 1. What's velocity times time? I move at 3 meters per second for 7 seconds. Haven't I moved 21 meters? So isn't this now the distance that this bar is traveling? All right, keep that in mind. Let's now put this bar on conducting rails. Isn't velocity times time the distance that that bar has traveled? And the length is the height of that bar. So if we have the height times the distance it's traveled, isn't that the area? So this becomes the area times the magnetic field over our time. Well, what is the area times the field? It's perpendicular. Remember doing that? We talked about the electric field through a closed area. What did we call that? The electric flux. Wouldn't that be the magnetic flux? What we would find out is the induced voltage in a loop is equal to the change in flux with respect to time. It works out this is not just true for a bar that's moving through space, it's true for any loop. If we have a changing flux through a loop, it will induce a voltage. I should say a changing magnetic flux. So we can do that several ways. We can make the loop bigger, like we did here, and we'll induce a voltage. We can change the magnetic field and hold the loop stationary. Or we can take and move this loop through a non-uniform magnetic field. This is known as Faraday's law. So a changing magnetic field induces a voltage. In other words, it creates an electric potential. There is a connection between an electric field and a magnetic field. The induced electric voltage, we can generate an electric voltage by a changing magnetic flux through a loop. The last thing it talks about in the note is in circuit theory, this current will be limited by R. Since this is positive, won't current flow through this loop? That'll tend to reduce the voltage, but then the electrons will get pushed back down and the protons will get pushed back up. So the current will continue to flow in this loop, maintaining that voltage. The current will be limited to the resistance of that loop. Now, we're generating electricity. There's now a current induced in that bar. We're creating electric energy. There's a force on that wire. I is up. So now we have I through a magnetic field B. Which direction is the force on that conductor that's moving through? The magnetic field with the current through it. Now the force will be opposed to the direction of motion. That means we have to do work to pull that bar through the magnetic field. Amazingly, if you go through the math, the amount of work we do pulling this bar is equal to the electric energy generated. So there is conservation of energy. Any questions? So we are almost done. How would we find out the current out? I think I'll just go ahead and introduce this idea right now. The direction, there will be a voltage induced now when we have a changing magnetic field. In this case, we have a loop of conductor. We have a field coming out through the conductor. The magnetic field is increasing. is the flux through this loop increasing? We have a loop of wire, and our loop. Field's coming out at you, and the field is increasing in strength. Yes, the flux is increasing. Will there be a voltage induced? Yes, and that voltage induced will be the flux, which is the area times the rate of change of B. So if A is constant, this could be equal to A dB dt for constant A. It could be equal to B times dA dt for constant B. Or it could be just the change of flux if both are changing. So in this case, our area is not changing, the flux is changing, the field is changing, and the flux is changing. What about this case? Is it a voltage induced in this loop? Will there be current flowing in it? Yes. What about this loop? By the way, when you see this, that's this loop here, rotated 90 degrees. Is the field changing? It's changing at half a Tesla per second, but it's not going through this loop. There's no flux. Remember that flux is that component of the field perpendicular to the plane or parallel to the area vector. It's still B dot A. Our integral, our flux is still our integral of B dot dA. So if we wanted to find the induced EMF, we'd need to know the area, we'd need to know the rate of change of flux, what they're telling you, and then if you know the resistance, you can divide the voltage by the resistance to find it. What direction does the current flow? Let's think common sense wise. If current flows in this direction, which direction will the induced field be through the loop? It'll be out towards you, right? So as the current increases in the loop, what will it do to the flux through the loop? It'll increase it. So that would mean that, the current would increase some more, right? And we'd be getting something for nothing. What we know is that the current will be formed in a way that opposes the change in flux. This is a name, Lenz's law. So if the field is increasing, the current will be induced in a direction to decrease the flux. If the flux is decreasing, the current will be induced in a direction to increase the flux. So the current is always induced in a direction to oppose the change in flux. Now, the only way to really learn this is to go through and practice. So I will try, I'm slowly slipping behind. Confusing stuff. EMF and voltage. EMF is an old phrase. You don't even, the textbooks don't even tell you what it stands for because it even adds confusion. But EMF is synonymous with voltage. Voltage is a potential difference between 2 points. EMF implies that it's a generated voltage or generated potential difference. But we may use all of these terms interchangeably, and the physics behind them, the concept, the fact that it's a difference in potential is the same. So we're talking about the same concept. Historically, a lot of different words, a lot of different symbols, but it's really the same thing. Physicists tend to like the change in voltage to emphasize that we're really measuring the potential difference. Circuits people get lazy, they don't like to write the deltas, so they write V, but it really is a change in potential. Same with the script E or EMF, it is the change in potential between 2 points. Generally, if it's an EMF or a script E, it implies that it's a generated EMF. In other words, it's from a changing flux. But it's the same concept, it's just created in a different way. Why do we care? Motors and generators. Do you guys have any idea how many motors are in modern cars? There's hundreds in some of them. Run your windows up and down, everything. Oh, there's CD players, your starter, there are just a number, your wiper blades. There are many, many moving devices. Your little controllers on your windows, so when you adjust the windows, there are many, many motors. Generators convert mechanical energy to electrical energy. Motors convert electrical energy to mechanical. They're oftentimes the same device, it's just which direction is energy flowing. So the construction is usually very similar, identical. Energy is conserved on all of these. We don't get energy for free. So we have mechanical energy in, there's some losses, we get electrical energy out. So that would be a generator. Or if we have a motor, we have electrical energy coming in, we have some losses, and we get some mechanical energy out. In a motor, the mechanical energy out is less than the electrical in. In a generator, the mechanical energy in is greater than the electrical energy out. Right. Reminder, this was an electric field, but it could be a magnetic field. We look at the normal to the surface, that is our area vector for the surface. We're interested in the electric or magnetic field that's in the direction of that area, or so we look at the angle between those two vectors, and the flux will be the dot product. We have to have flux in parallel with area vector, or in other words, perpendicular with the surface. That one. We went back, we reviewed those. Faraday's law. If we have multiple turns, each loop generates the same voltage. So if we have 6 or 7 loops, and we have a changing flux through those 7 loops, we will induce 7 times the voltage. Lenz's law tells us that we don't get anything for free. The current will be induced in a direction to oppose the change in flux. So we have a changing flux through our loop. The current will be induced. It will be induced in a way to oppose the change in flux. And you really understand that in the practice. So we'll pick these up with clickers. We have a north pole that's that's facing these coils. The coils are going in this direction. What is happening to is there a magnetic field through those loops?
Yes.
Is there a flux through those loops?
Yes.
Yes. Is there an induced current? No, there's no induced voltage, there's no induced, why not? There's a field through it. It's not changing. The answer is not changing. No current. Now, we're going to move the magnetic field, or the magnet to the right. Now, is there a magnetic field and flux through those loops?
Yes.
Is it changing? Yes, is it increasing? It's increasing in that direction or that direction? Left or to the right? To the right. So the current will want to be induced in a way to oppose that change. So we want the current to be, we don't want to, it just is, induced to the left. The way to read this is the fatter lines are the ones that are closer to you, the thinner ones are behind. So the current should be going to the left. Right, so the current will come up here, go around the loops that way, creating a magnetic field that opposes the change. And the magnitude of the induced voltage and current will increase as the faster we move the magnet, because the rate of change in the flux is increased. Any questions? What we will do on Monday is continue to go through these, and I'll go through as a practice quiz. I'll want to hit it right out of the gate, and then we'll have a quiz. This is posted online. You can go through it. You can go through a practice yourself, but we will go through a practice one more time in class, and then